Okay, so I'm just gonna go ahead and start. I feel kind of badly that there's not actually that much in the way of like true mathematical content to the lecture that I'm gonna give today. But yeah, I mean, I think we're sort of entering a realm where a lot of what is known is mostly not actually known, it's more just like empirical. And so I'm going to try to say some things, at least from this particular source that I was looking at for today's lecture, after I tell you a little bit about the attention mechanism. So, okay, so if you recall, the basic structure of a transformer is, so you have some set of tokens that is fixed in advance. You can think of them as being words, even though that's kind of a lie. But you've got some set of tokens, and the size of that set I'll denote that way. And so these tokens are embedded in the space in a one-hot way. So you start by ordering the tokens and then associating to them each a one-hot vector. And then you have some encoding layer, which maps all your tokens into this, what's called the residual stream, at least in this paper that I'm following. So by the way, I'll write it over here. It almost looks like a blog post, but it's called Mathematical Framework for Transformer Circuits. Okay, so you now create some lower dimensional embedding of all of these tokens into some slightly lower dimensional space. And then you run this through an attention layer. So each of these you should think of as computing something different. And all those computations are being done in parallel. And then you have multi-layer perceptron, which is the kind of gadget we were studying at the beginning of this course. Just you should think of it as just a ReLU neural network. And then you're again, well, actually in here as well, you're back in the residual stream. So always you have some layer and then you're back in the residual stream, and then you have another layer and you're back in the residual stream. And one of these blocks is what's called a residual. These repeat. So if you have more residual blocks, repeat to get a deeper network. So just very basically, this is the kind of structure of a transformer. And then at the end, you do an unembedding. And you're back in a space of dimension the number of tokens, and then you apply softmax to get a probability vector. And then the token with the highest probability wins. That's going to be the next output. Okay, so last time we talked a lot about this, you don't have any of this stuff in between. Really, somehow what this transformer is doing is learning a good embedding of the tokens into some slightly lower dimensional space. But something that I didn't really mention, but that I should mention is some important heuristics. And probably you've heard some of these, but if you haven't, it's important to keep them in mind. is that so you can have this residual stream. So this is the embedding space where the tokens live. And you should think of this first embedding, which again is just a linear map, produces what you might call a context-free embedding. Of the tokens. Somehow it's believed, and it's certainly used as heuristics, that there is some geometry, well, some of the geometry of this residual space, this embedding space, actually captures relationships between tokens. So, so when I say context-free, I mean before you started attending to other tokens or taking anything into account about the actual sequence you're feeding in to the transformer. So there are kind of precursors of this. I think the most famous early one was word to vec, and that produced from, I mean, collections of tokens, but that weren't in any kind of sequence order. Embeddings into some space in this way. And it was observed even back then that, that relations between the images of these tokens actually tended to correspond to relationships between tokens. So the sort of famous, so I'll just say the sort of informal belief. And again, this is sort of purely empirical in a lot of, so there's empirical evidence. And the relations between tokens can be captured by the geometry in the space. So I think the most so if you look at the image of woman, and you subtract the image of man, and you add that to king, then that ends up being very close to queen in this space. Things along this line. Things along this line. So I mean, I'm like somewhat skeptical of this actually being a thing. I mean, like, sorry, not of it being a thing, but of it being something that you could actually mathematically characterize using just sort of linear operations in general. I mean, I think that there are some observations, and it was very exciting. But I don't think something like this is true, sort of in the greatest generality. Probably very, very simple relations might be capturable in this way, but more complicated relations, I'm sure somehow are probably not going to be. Yeah, there's not going to be like a theorem here. Okay, and then yeah, and the other thing that is part of this informal belief is that nearby embedded tokens should have similar meaning. So again, these are really just heuristics, but I think that they're useful for So in this embedding space, you would hope that something about the geometry of the space is capturing something about meaning, I think is how I would summarize what I'm trying to say here. Okay. And then, so I'm about to tell you about attention. And so I'll just say that somehow what we should be thinking about is that these attention blocks adjust the embeddings of the tokens in response to the context. So the attention mechanism is some way of taking these embeddings, these original embeddings that were context-free, and then using the information of the sequence, so the embeddings of all of the tokens in the sequence, to adjust the locations of each of the tokens as you move through. And I guess I should say also that the MLP layers do as well. But somehow I think the heuristic we should have in mind, or I guess, again, the informal belief, is that the MLP layers are doing more of the sort of reasoning, the actual reasoning that's happening in the transformer. Although, I would say that evidence there is also somewhat thin. And probably that most of the evidence comes from the fact that if you get rid of the MLP layers, the transformers don't do a very good job. All right, so now that I've kind of sketched out what the heuristics are, let me tell you about attention. So attention is the really new mechanism beyond what we've talked about so far in this class. So I said that each attention block is made up of a bunch of attention heads that are running in parallel. So let me just describe a single attention head. So imagine that the input to a single attention head is just this dr by n matrix. So remember, dr is the dimension of the residual stream. And n is the context length. So it's the number of tokens in the sequence that the transformer is reading in. Okay, so the input is the dr by n matrix. And I'll label the columns E1 through En. So these are the images of the embedded tokens. So think of these as, at the very beginning of your transformer, after you've done your embedding. Those are the images of the tokens. So now what we have are, so associated to this head, let's give the head a name, let's call it H. So we now have two matrices, WQ and WK. So these are going to R. But somehow, usually DQ is the same as DK, is the same as what I was calling DV last time. And this, by the way, is usually much smaller dimensional. So these are very skinny matrices. I think that I was saying this is like 128 when DR is like 20,000 in GPT-3. Okay. What are these matrices for? Well, basically, they're to produce a map of these embedded tokens into this lower dimensional space. And really, these are kind of the same space. I mean, they're not, but they're isomorphic. Okay, so these are low rank maps. So you do this and then you compute pairwise, all of the pairwise dot products. So we use WQ and WK. So apply WQ and WK to, let's give this matrix a name, let's just call it big X. So this is just the set of tokens. And compute all the pairwise dot products. So you can do this in a really compact way. So, essentially what you're doing is you're taking WQ, you're multiplying it by X, which just does, so now each column of this is each of the images of the tokens inside this lower dimensional space. So the columns of this are the columns WQ, right? And then you're taking the dot products with the applications of WK to the embeddings, which are the columns of X. So the point is that the rows of this matrix are the images. Look here. The rows are the images of the E eyes under WK. Okay, so yeah, this is just WK times X transpose. It's the transpose of a product, the product of the transposes. Okay, so now what do you have? Well, you have a matrix whose rows are the images of the EIs, and you have a matrix whose columns are the images of the EJs under the Q matrix and the K matrix respectively. And so when you take their product, these are the pairwise, the entries are the pairwise dot products. Because a row here is multiplied by a column here, etc. as a dot product. Okay. So the point is that the ij entry of X transpose WK transpose WQ X is the dot product of EI of the image under WK of EI with the image under WQ of EJ. Okay, so now you've computed these pairwise dot products, but now you want to turn it into so what you're trying to use these pairwise dot products for is you're trying to so for each EJ, the column associated to EJ will determine so the ordering of the entries in terms of size in that column will determine how much token J will attend to token I. So what we want to do is turn this into an actual probability matrix, and we do that by then applying softmax. But there's still another step. So let me erase this. So we want to turn this into a matrix where the columns are probability vectors, but we want to do it in such a way that it's going to be upper triangular. And remember, the reason for that was that we only attend to tokens that are that we've already seen in the string. So then you apply what's called masking. The lower triangle entries. By setting them to negative infinity. So what you want is that when you apply softmax, those entries will become 0. And then apply column-wise softmax. So we have this XT. Then you mask. Then you apply a column-wise softmax. All right, and the idea is that when you do this, what you've produced is a matrix where each of the columns is, so it's a upper triangular matrix, where each of the columns represents how much the token associated to that column is going to attend to other tokens. So in column 1, the first token can't attend to anything but itself because there's nothing to the left of it. And the second token can only attend to itself and the first token, etc. Okay, so so this is now called the attention pattern. And it's completely determined by these pairwise dot products of the projections of tokens to lower dimensional spaces somehow.
What does the H stand for?
This is just the labeling for the head. Yeah. So yeah, if we call it head H, then this is the attention pattern for head H. Okay. All right, so that's one part of the calculation. And then the other part of the calculation is determining how it is that we're going to adjust the embeddings of the tokens based on this attention pattern for this head. Okay, so that's the first part. And then the second part is maybe I'll just say the entry in the ith row column of this attention pattern associated to the head measures the proportion of the attention on EI for computing the update. To the embedding of EI. Okay, but then what is that update? Well, that's computed by this this product of an output and a value matrix. So to compute the update, now we have these two matrices that we'll call WO and WV. And really they only appear as a product. And so now associated to each token, you compute an update by applying WV and WO. And that's the update associated to that head for that token. And so now if you have a token EI, then it will get sent to WO, WV, EI. So this is the update associated to token I.
Still linear maps?
These are still linear maps. Yeah, it's amazing, right? Everything is linear. The only thing that's non-linear in an attention head is the softmax, the masking and the softmax. That's it. So then we can compactly write what the output of head H is. So let me do that. So you have your matrix X, whose columns are the embedded vectors, or at least the embeddings so far of the tokens. And then you have this attention pattern that you computed from the query matrix and the key matrix, the WQ and the WK. And then over here you have WOV. Okay, so essentially this part is computing what the updates that are coming from the head will be. So this part tells us what the the updates are associated to each token. So the columns of this are those updates. And then this tells us, this tells us how much to use each of those updates for each of the tokens. So let me just give a concrete example so that you can see what I mean. So this looks basically like WOV times E1, WOV times E, and times this attention pattern. Okay, and if this attention pattern, so for example, if the attention pattern was like, so it can only be 1, 0, 0, 0 in that first column. And if it were like 0.9 and 0.1 here, then this would look like the first column here would be WOV V1. And then the second column would be 0.1 times WOV, no, 0.9, sorry, times WOV E1 plus 0.1 WOV V2. And this you're actually thinking of as being the delta X. So you're going to add this to your X matrix now. So after the head, it becomes X plus delta X, where this is the delta X. This is the update. This is the update associated to the head. So we had our original X, and now we'll add this to it. We do that for each head in this set of parallel heads. So delta X H. It's the adjustment. Embedding the tokens in X in response to this query key output value. Response to H, to the head H.
Ellie, in your example, can you re-explain what WOV really is doing? Because it seems to me like the 0.9 and the 0.1 are doing the job of updating or telling us how much to update, which is coming from AH, not WOV.
Right. So, right. Great question. So, so the point is you don't want to update by the embeddings themselves. You want to update by something that you're extracting from the embeddings. So it's this matrix WOV, which is a projection of EI into a lower dimensional space and then a re-embedding back into your residual stream. So you're actually doing something when you apply WOV. So WOV times E1 is definitely not going to be E1. So you really need these outputs and values to do the adjustments. We're not doing adjustments by the original embeddings. We're doing adjustments by these, by the images of these embeddings by this output value matrix. Yeah, so the attention head has two different jobs. One is to decide what to attend to among the previous tokens, and all of that is governed by the query key, which again are like dot products in lower dimensional spaces. So it's, it's mostly that. And the output value is just telling us how to take our embedding and map it into some lower dimensional space in some way, so that, map it into a lower dimensional space and re-embed it into our space in such a way that it provides the correct adjustment, whatever adjustment that is. Okay. So, all right. So yeah. Anyway, this is an attention head. And there's, in a certain sense, a lot going on. Yeah, go ahead.
So the output is really X plus delta X H.
Yeah. So if there was just a single attention head and a single attention layer, then the transformer would, the output of the matrix run through that layer would just be something that looks like that. And now you have a bunch of heads running in parallel. You're still just adjusting by each head. You're adjusting your original E1, sorry, you're adjusting your original matrix X by the sum of every contribution from every head. So that's really the bulk of the mathematical content of this talk, or this lecture. Let me just make a few remarks, which are somewhat semi-mathematical, but that I think are interesting to just point out. So you might notice that AH and WOV act on opposite sides. X. They're multiplied on opposite sides. So these actions commute. These are commuting actions. Because matrix multiplication is associative. So that's just kind of interesting to note. And in fact, this is somehow computationally why these attention layers are so nice, because all the computations can be done in parallel. So this is not just mathematically interesting, and I really do think it is mathematically interesting. I mean, if they were the same dimension, that would mean that they were simultaneously diagonalizable, for example. But they're not the same dimension. So, but anyway, they are commuting. Okay. So, and the fact that they're commuting has great implications in terms of being able to actually implement attention layers, because the computations can be done in parallel. Yeah, and same with the computations for all of the heads separately. Like everything can be done in parallel, everything commutes, because when you put things together, you're just adding them, and that also commutes. So, everything is really nice in parallel. So this is going to be a mathematically imprecise statement, but I hope that it's still interesting to make. Since WOV is a low rank matrix, so essentially what you're doing, as I said, is taking your embedded tokens, you're mapping them into some lower dimensional space, and then you're re-embedding that lower dimensional space into your residual stream. So now you have the images of all of these tokens now is in some very small dimensional subspace of your original space. So whereas your original embedding might have put everything kind of like filling out your space, these images, the images of your output value, well, of each head are always sort of sitting inside some lower dimensional space, very lower dimensional. So it's a low rank matrix. The adjustment to each token is in some sense sparse. Embedding. When I say the adjustment, I mean what I'm calling delta X. Each token embedding is sparse in some sense. Okay. And here's a third remark that that was in this blog post from Anthropic, or this article. Each attention head be regarded as contributing solely to what they call skip 3-gram statistics. Yeah, I'm gonna try to say what I think they mean. So we talked a little bit last time about bigram statistics and how before you apply any attention, somehow what the embedding and the unembedding should be measuring is the bigram statistics. So skip 3-gram is so you so to determine the output, you just look at 2 elements of the input, but they don't need to be consecutive. So that's what they mean by skip trigram. So so if you have your original sequence of token, so this looked like this list of tokens. So remember, the task is to predict the next token in the string. And attention, I mean, somehow this statement is not much more than saying that for an attention head, a token is getting updated by looking at just a single token. Sorry, what am I actually saying? So I mean, the way to understand how this is updated is by looking individually at each of the other tokens before it. And then each of those is going to form some gadget that we call a skip trigram, which is basically a pair of tokens in the context that are altering the prediction. So I'm not saying anything as precise as what I said last time for bigram, but yeah, the point is that the attention patterns are identifying how pairs of tokens, not necessarily adjacent, adjust the bigram statistics to give you these skip trigram statistics. Okay, so maybe I'll just so here are some empirical observations that they pointed out. So one empirical observation from the paper. One experiment that they did is that for each head, they looked at, so this is what they call the source token. So they call their destination token. And then you have the output, which affects the prediction. So the delta X. That's delta X. Delta X, delta EJ. And what they found is that very often, right, so they looked at large entries of the attention pattern. So yeah, looked at large entries of the attention pattern that also simultaneously had the source token as a large delta X. So WOV of I. This is large, measured in terms of, I guess, of the norm. Say something like the ith column delta X is large. And what they found when they looked at these is that very many of these have the effect of being close to, so the resulting prediction ends up being so the sort of informal statement they made informally. Is the following: tokens, if attended to by a head, tended to greatly by a head, increase the probability of that and similar tokens being predicted. So essentially what they're doing, what they find that attention heads, single attention heads tend to do is actually copy source tokens. So somehow what's happening is that when a head attends very much to this source, it doesn't really matter what the destination is. All that seems to happen is that it predicts something close to that source. So essentially what's happening is that, yeah, because that output value is large, you get it. Again, I'm not saying anything like super precise. I'm just, tokens if attended to greatly by a head increase the probability of that and similar tokens being predicted. So they have some examples. They list some source, destination, and output tokens. So essentially what they do is they train a one-layer transformer, say with multiple heads, and then they just look at the attention patterns for the various heads, see where they're large, and if the source token also is large, then it has this behavior. And that definitely makes sense, because if the source token is large, it's going to adjust things in a direction that is very close. I mean, if we believe this heuristic that positions in this embedding space actually correspond to meaning, and that if things are close to that, then it will get moved to that, or it will have a similar meaning to that. So the examples that they give, WY is perfect, WJ is one of these, R looks, is, provides, and then the prediction is. So all it's doing is copying the source. There are other examples, but it was interesting that they found that this happened quite a bit. Let's see. Let me I'm gonna end soon, but maybe like the last thing that I'll say is that there's sort of a nice at least picture that they have in there for how to understand what deeper attention only transformers, or kind of how to understand deeper attention only transformers. So then, let's say it this way, the updates associated to deeper attention only transformers. Can really be understood or represented by considering sort of paths through your network. So I'll just say what I mean for a two-layer transformer, two-layer attention-only transformer. And let's just say we have a single head. But it's not much different if you have multiple heads. But the idea is that that because right, you also have the embedding and the unembedding. So the idea is that because really you're always carrying through your original embedding through the whole matrix and through the whole computation, and also the attention pattern acts on one side, on the right side, and the output value calculation acts on the other. You can really kind of think of it as being this sort of, you can represent it at least, this map here, through this attention head. Sorry, I should have actually written it a different way. Call this head 1 and head 2. This map is really the identity map plus the action of this sort of right action of the attention pattern associated to that head, and the left action of this OV matrix. So yeah, if you start with this, sorry, this is not in here. If you start with this list of vectors in here, then you act by this. You can decompose the composition just by kind of multiplying out the different compositions, or sort of the different ways of getting from here to here. So all I mean, so this tensor product just means act by this on the right and act by this on the left. So if you wanted to understand what's happening in a 2-layer attention-only transformer, you have and somehow the point is that you have these, you have this first term, which we've already discussed, which is just moving through without doing anything. And that's where you're factoring through the identity in each of these terms. And then you have the terms where you factor through the identity in one of them, but then the attention head in the other. So these are where sort of these skip trigram statistics show up. You always WU and WT. And then you have the interesting term where you're factoring through 2 attention heads consecutively. And what's interesting there is that these matrices just multiply. And again, these are stochastic matrices, so their product is also a stochastic matrix. Sorry, these 2 matrices are stochastic matrices, so their product is also a stochastic matrix. And these are, again, these 2 different, like, low rank matrices. But the point is that that you get something that you might call, and this paper calls, a virtual attention head. It's sort of the thing that you get that really still looks like an attention head. So So the structure of mapping through a bunch of attention heads really is preserved. It really looks like the same thing. This is still a stochastic matrix, and this is still a low rank matrix. Okay, so I think I will go ahead and end it there.